Okay, in this section we will discuss electric potential at a point. We'll try to define electric potential, we'll try to get an expression for it, and obviously we'll also determine a relationship between the electric potential and the line integral of electric field. But before we proceed with the electric potential, let's recall electric potential difference. Now, electric potential difference between the 2 points A and B, A is the initial point, B is the final point, is defined as the work done per unit charge in bringing or moving this charge from one point to another point. And we have obtained an expression for the potential difference as well. It is negative of the line integral of the electric field between A to B, which in turn is also equal to, this is the expression basically, 1 by RB minus 1 by RA, right? This was the expression for the potential difference which we have done. Potential differences between any 2 points. Now let's come across this topic, electric potential at a point. So our objective is to find out the electric potential at point B. So what we do is, we'll consider point A to be located at infinity. We'll consider point A to be located at infinity. In that case, potential at point B is defined as work done per unit charge in bringing this charge from infinity to that particular point. From infinity to that particular point without any acceleration. Without any acceleration means while moving the charge Q0 along any arbitrary path, the net force acting on that charge Q0 should be 0. So it has to be moved without any acceleration. So the electric potential at a point is defined as work done per unit charge in bringing this charge from infinity to that particular point without any acceleration, right? So now let's obtain its mathematical expression and let's get its relationship with the line integral of electric field. So simply what we need to do is that in order to determine the total amount of work done, we will first determine small amount of work done in moving this charge from P to Q through small distance dl, right? So small amount of work done in moving this charge Q0 from P to Q against this electric force of repulsion would be given by F dl, scalar product of force and displacement. Now look, if this test charge is left free over here, due to this positive source charge, it will experience an electric force Q0e along the direction of the electric field. Now in order to move this charge Q0 without any acceleration, the net force over here should be 0. So the force that needs to be applied is Q0e in a direction opposite to that of the electric field. So here the force which is to be applied so as to move the charge Q0 without any acceleration should be minus Q0e. Minus sign suggests that the force is to be applied against the direction of the electric field. Dot dl vector. Now, if we integrate, we'll get the total amount of work done. So on integrating, what we get is Q0 is constant. And total amount of work done is to be found from infinity to that particular point. So from infinity to RB. From infinity to RB. So what we get is total work done, infinity to point B, it will be equal to minus Q0 E vector dot dl vector. Limits will be from infinity to RB. So it may be written as negative of line integral of the electric field. Limits will be from infinity to that particular point. Now look, put this as equation number 1 and this as equation number 2. Now from these two equations, what do we conclude? We conclude that the potential at a point is given by, just make use of these two equations, negative of the line integral of the electric field, E vector dot dl vector. Limits will be from infinity to that particular point. So this is an important relationship. So this is the relationship between the potential and the line integral of the electric field. So let me conclude it. The electric potential at a point, this point is considered point B. The electric potential at point B is numerically equal to the negative of the line integral of the electric field between infinity and that particular point. Right? So this is a very, very important relationship. Put this as equation 3. Now let's find its expression, and that's again very simple. What we do is, we are already aware of it. E vector dot dl vector, we have already obtained its expression. If it is Ra to Rb, then its expression is Q over 4 pi epsilon 1 by Ra minus 1 by Rb. This we have already derived in the previous section, right? So here the limits are from infinity to Rb. So in place of Ra, write as infinity. Ra should be replaced by infinity. 1 by infinity is 0. So infinity to Rb, E vector dot dl vector will be left with minus Q over 4 pi epsilon Rb. Put this as equation 4. Now compare these two equations from 3 and 4. We get potential at point V is equal to negative, and this negative get cancelled out. We get Q divided by 4 pi epsilon Rb. So this is the expression for the potential at point V. Now let's discuss its SI unit as well. SI unit of the electric potential difference or electric potential, it's same. It is volt. So 1 volt is equal to 1 joule divided by 1 coulomb. So let's discuss its SI unit and let's try to define it. So SI unit of potential or potential difference is volt. SI unit of work is joule. SI unit of charge is coulomb. So question may be asked कि when the electric potential at a point is said to be 1 volt. So the electric potential at a point is said to be 1 volt when 1 joule of work is required to be done in bringing this charge of 1 coulomb from infinity to that particular point without any acceleration, right? And then we have already discussed its CGS unit. The CGS electrostatic unit of electric potential is stat volt. The CGS electromagnetic unit of electric potential is ab volt. We have discussed its dimensional formula as well. Joule in terms of basic units, it may be written as kg meter square per second square. Coulomb, it may be written as ampere second. So it will become kg meter square s to the power minus 3 a to the power minus 1. So the dimensional formula for electric potential difference or electric potential is the same. N L2 T minus 3 a minus 1. So this is the dimensional formula for electric potential, right? So we have discussed 3 very, very important topics. Electrostatic force, which is the Coulomb force, then we have discussed electric field, then we have discussed electric potential difference, and then we have discussed electric potential. Let's recall those topics. Basic formulas, let's recapitulate it. Now suppose these are the 2 point static charges, Q1 and Q2. They are separated by distance r, right? So the electrostatic force between these 2 point static charges is given by K Q1 Q2 by r square. In case they are placed in vacuum, then K would be equal to 1 over 4 pi epsilon naught, which is the absolute permittivity of free space of vacuum. In case of a source charge Q and observation point P placed at a distance r, the electric field at this point due to the source charge would be given by K Q by r square. Right? This is the expression for the electric field. In case this is source charge and this is the observation point, the potential at this point due to the source charge is given by K Q by r. This is what we have discussed right now. This is the formula which we have discussed in this particular section. This is the potential at point P. Potential difference between A and B. This is Q. This is suppose point A. This is suppose point B. So the potential difference would be given by KQ 1 by RB minus 1 by RB. So these are very, very basic expressions for electrostatic force, electric field, electric potential and electric potential difference.